Hello, welcome to the Accumulator Overview Presentation. So today we're going to be going over uh, all a high-level overview of Waterloo Formula Electric's accumulator. This is a high-level overview. It won't cover our entire uh, electrical infrastructure. And to have a good understanding of our infrastructure, you're probably going to want to read up on some of our documentation on our low voltage system. For those who don't have access to Confluence and perhaps non-Waterloo students, that won't be available to you. But for those who do, I have written up a presentation on the firmware overview of the vehicle for non-technical drivers, which is very helpful, as well as I have an overview of all the acronyms, terms, and definitions that we use on the team, and our ESF2, which is a document we submit to the Formula Hybrid Rules Committee, is a great depiction of our entire electrical infrastructure. So without further ado, we'll start. Before we go on to learn about the actual accumulator, I think it's important to go over some, I guess, high-level safety concerns. So we are dealing with a quote-unquote accumulator, we call it, which is essentially a high-voltage battery. And whenever we're dealing with things that are high voltage, we have to add an extra layer of precaution because there's potential for danger to damage to equipment as well as damage to human beings. Especially our high voltage battery is very dangerous as it has a very large capacity combined with a high voltage, which is lethal. So the biggest danger probably is electrical shock. An electrical shock across the human body can cause permanent brain damage and death. This is very extremely dangerous. I don't think anyone wants their last moments to be in the Formula Electric design bay. So we have to be very, very careful when dealing with this stuff. To sort of give you an idea of how dangerous this stuff is, a human body resistance can fluctuate between a kiloohm and 100 kiloohms. But I mean, as soon as you're touching high voltage, the skin contact resistance is going to be burnt away, and that resistance is going to drop tremendously to something like 500 ohms. So with our 300 volt accumulator, you're going to get about close to 600 milliamps flowing through your body, which is very high. That sounds like a very low amount in the milliamps, but 1 milliamp shock you would feel it. You'd be like, ow. At 10 milliamps, you're losing control of your muscles. 30 milliamps, you stop breathing, and then 75 milliamps, ventricular fibrillation, and you're dead within minutes. And one of the issues with electric shocks is once you grab onto something or once you touch something, it's very difficult to let go, and it's all about the time. So if anyone is ever in electric shock, it's extremely important to remove them from the electric shock without involving you in the circuit. So that's a big piece of information. Specific procedures will be done on a person-by-person basis in the Formula Electric Bay, and I don't think I'll be going over them in this presentation. So another issue is thermal runaway. So we use lithium-ion batteries. We use a Samsung 30Q 18650s. Lithium-ion batteries, when damaged, can undergo thermal runaway, which is essentially if they're damaged at all, they attempt to release all their energy at once. And lithium-ion batteries are very energy dense. So this can cause electric fires. It will release toxic gas and can sometimes cause explosions. We have 490 cells, so you can imagine this runaway occurs very quickly and spreads very quickly. So 490 cells, one cell gets damaged, it causes a fire or releases gas, which transitions to the next one, and eventually the entire accumulator is damaged and is extremely dangerous. One thing to be aware of, if there's an electrical fire with the accumulator, you cannot use water to put it out. If you go and throw water on this electric fire, what's going to happen is now you've just created a pool of conductive high voltage liquid. Not a good idea. You can try to use a Class C fire extinguisher, which are rated for these sort of things, but honestly, it's not going to happen. If our high voltage battery gets under thermal runaway, the best thing is move away from it. If it's possible, push it out into an open space. But really, it's make sure it's not going to spread, contact the authorities, and don't put yourself in harm's way. Additionally, we want to make sure we don't let anything get dropped in the accumulator because it can be very bad. Any small thing that could cause a short could cause a thermal runaway. So dropping a nut in the accumulator is very bad. Please tell one of the leads immediately if this ever happens. If you ever see anything get dropped in the accumulator, we have to deal with it immediately. So these are some of the rules. I don't think I want to go over them because these are subject to change. But basically, unless you're trained, unless you're one of the certified people, don't go touching the accumulator without permission. When we're dealing with the accumulator, we're going to do it in a wide open space. And we don't want anyone near us when we're working on it to prevent bumps or perhaps like conducting if there was a actual electric shock. Whenever we're working on the accumulator, we have to have someone with us in case something goes wrong. We need someone to assist us. If we grab onto something and we lose muscle control because of electric shock, it's critical someone's there to push us off. And we always have to make sure we're using the proper tools. So high voltage insulating tools like Allen keys, safety glasses, and high voltage gloves are what we're doing. And yeah, whenever the accumulator lid is off, have the high voltage blank on it, have fire extinguisher. And if there's any potential safety concerns, report them immediately. So that's the main safety section done. Now we're going to go over our accumulator. So we'll start with the box. This is a picture of the lid of our accumulator, our current one for the 2022 season. So this is on top of the accumulator itself. So here we have, there's the handle on the right-hand side, and then there's two large orange connectors, the positive connector and the negative connector. So these are our high voltage cables, which go from the DC output of our battery box, our accumulator, directly to our motor controllers, also known as inverters. So that's our main current carrying path. On our main current carrying path, we also have an HVD and HVD key. So basically what this is it's a device that connects the circuit. So when this is removed, no current can flow. And when it's put in, it's a method that object in our high current path. We have an HVD interlock. This is a special key where if this key is removed, it will disable all high voltage in the system through the interlock loop, which is a low voltage interlock loop, which is a automotive device, which will be dealt with in another presentation. But it's a very useful safety feature. So when you pull out the HVD interlock key, ideally, all the car will shut down, all the high voltage systems will shut down, and then you can safely remove the HVD knowing there will be no high voltage current passing through it. But it's also an extremely safe HVD design. We have the DC-DC output. So inside of our lid, we have a DC-DC, which essentially converts our accumulator voltage of 252, 300 volts from that voltage down to 12 volts, which is used throughout our low voltage system bus. So it basically takes some of the load off of our low voltage battery so it can last longer. We have a charging port here. That's essentially pretty self-explanatory. When we want to charge, we plug into there, and that just connects to our bus bars so we can charge the actual pack. And TSMP connector. So the TSMP is basically, it's called a traction system measuring point. It's a box we have in our car, which breaks out like our traction system positive, our high voltage positive, our high voltage negative. So we can easily measure that outside of the car and check for potential isolation faults and such. There are also these buttons right here. I won't go over them, but there's the accumulator indicator LED, which tells us if the vehicle bus is at a high voltage, and then some buttons which perform necessary relay and interlock completions. And right here in the middle is our low voltage connector, which connects to our BMU, our battery management unit, which is a PCB that manages the accumulator. So that low voltage connector connects that to the rest of the vehicle. Yeah. So a sort of high level overview of our accumulator setup. I went a bit over it, but here's from a very, very high level. We have our accumulator here. Our low voltage bus is 12 volts and it connects 12 volts, and we have ground. So there's our low voltage bus. We have our DC-DC output, which supports our 12 volts bus when we're quote unquote pre-charged. When our high voltage bus is activated, it will support our low voltage bus. And then we have two motor controllers, which are connected to our high voltage connections. So that's a high level. A more in-depth diagram is given here. I won't go over this. I think it's just a very good diagram, which it doesn't tackle everything inside of our accumulator box and lid, but I think it does a good example of showing, okay, here are the segments in our accumulator, AMS boards, how they communicate, where the various connections on these connectors go, and the contactors and pre-charge system. So I use the word segments. So I'll go into a little bit of depth of that. Our accumulator is divided into 5 quote unquote segments, which are essentially groups of cells which are connected together. So from a high level, we have the individual cell level, which are individual cells that are packaged into cell groups. So a whole bunch of cells in parallel that are then grouped in series into cell segments. So segments are groups of cell groups. Essentially, large collection of battery cells that we put together with the idea that we don't want to, if we need to service this, we don't want to be working on a 300 volt entire pack. We can break it apart, deal with individual segments, and it's nicer monitoring and just like general isolation, and as well as thermals. So this is a cross section. You can see here the Samsung 30Q cells inside the box. That's an example of what segments sort of look like on the inside. On our current accumulator, each segment is about 60 volts, so 98 Samsung 30Qs. We have 14 in series and 7 in parallel in each segment. So yeah, each segment has its own quote-unquote AMS board, so Accumulator Management System board, which monitors the cell voltage and cell temperatures for that individual segment in itself. And then we group these 5 segments together in series to produce our entire pack. So 60 volts peak for each segment, wire them in series, you get 300 volts. And we connect them in series together with something called SMDs, segment maintenance disconnects, which are essentially bus bars, which we put in and then we can remove to remove and attach the series connections. And just a little bit of an analysis for our accumulator. With these 70 total cells in series, we have 294 volts at our peak, a nominal voltage of around 252 volts, and our capacity is about 4 kilowatt hours. It's a little bit not a perfect estimation, as it takes into account certain losses and there's various quality of cells, but we're somewhere in the range of real capacity, 4 to 4.2 kilowatt hours, but on the actual track, I believe we will experience a higher capacity than that. Thank you for watching the Accumulator Overview presentation. I'll be doing the rest of the presentations. I'm putting them to YouTube as well. And this is also a Confluence page on Waterloo Formula Electric's Confluence. And I will be posting a PDF of that Confluence page in the description.